Hey there. Okay, next quiz video, which is connecting the electric field in a multiple charge situation with the force on a charge. So we'll have a part A and a part B. The first part, in order to make sure that you're absolutely clear before you begin, we want to know what is the total electric field at that point P, but point P is not a charge, it's just a point in space, right? So there's no charge there in part A. But then in part B, you're going to take a charge and place it at point P and see what happens based off of what you learned about point P in part A. So give it a shot. Okay, I'm going to start. Let's see, part A. You know what I'm going to do is I'm going to expand this so that we, like I prefer to do, so that we can see it a little closer. So one of the things that I had hoped that you would have picked up from our charge square video is the concept of symmetry. That can also be used here. We notice that we have a charge above and a charge below. We can use symmetry about the x-axis here. We would not be able to use symmetry if this charge and this charge were not both 3 nanocoulombs, or if this distance and this distance were not both 4 centimeters, or if this angle and this angle were not both 30 degrees. But they are. We can expect a mirror image of the influence from each of these, okay? So that we can get a sense of what direction the electric field is working due to the presence of each of these charges. So we're going to have, first of all, our electric field due to the negative charge, right? Which, if we want, we can go ahead and call charge 1. Let's go ahead and put that here. That'll be charge 1, and then this will be charge 2, and then this will be charge 3. So the electric field due to charge 1 will be pointed in the left direction because, let me center that a little better. Oops. That's okay. And the reason is because the negative charge pulls electric fields towards it rather than, pushing them away. So we would also expect one in this direction and one in this direction. Absolutely symmetrical. We know that there will be a x component to this field. Use my ruler. So you can see there would be an x component to the bottom field as well as an x component to the top field. And there will also be y components to each of these. But the upward y component of one field is equivalent and opposite in direction to the lower component of the lower field. So these two are going to cancel each other out. That's really good news for you. You can always use, well, you can't always use, but in symmetrical situations, you can use symmetry as a powerful tool to simplify your problem solving. It turns out in this case, we're not going to have to solve for any y components at all, only x components. There will not be any surviving y components. So let's do it. We want the x component due to the negative charge. We'll begin that by writing the electric field due to charge 1, the negative charge. We know that it's going to be in the left direction, and we also know that it'll be given by k times q1 over. It's always going to be 4 centimeters. Let's go ahead and solve this symbolically first, and then we can put in our numbers later. So We know that this will be the entirety of the electric field. There are no components to this one. We can now use the electric field magnitude of at point P due to the positive charge 2. In this case, we're going to have, it doesn't do any good to put a negative sign or a positive sign. Here it mattered because we had an actual vector and an actual x-hat direction. But this one, it's not x or y. It doesn't make any sense to have negative or positive. So instead, we're just going to use e, right? Then we'll break it up into negative, positive, whatever we need to do. Okay, so this one is going to have an absolute value of k q2 over r squared, where r here and r here are the same r. And when we decide to get our x component out of that, we can now start talking about vectors. It's probably cleaner for me to write the E field due to charge 2 in the x direction only. That will be kq2 over r squared times the cosine of the angle with respect to the x-axis here. So that will give us this component. It would also give us this component, but we're not really that concerned with that component, right? So that component then, these lines are parallel and the x-axis is parallel. This theta must be 30 degrees. So, okay, we have now the x component of the E field due to charge 2. We also know by symmetry that we have 2 of them, right? One due to charge 3. We can also say then that the x component of the E field due to charge 3 is also going to be the same as this. Now I could put 3, or if I want, I could just put 2 again. Nothing wrong with that, because they're equivalent, right? So the total E field at point P is going to then be k q 2 over r squared cosine theta minus k q 1 over r squared. And that will be in the x-hat direction. All of these actually vectors are in the x-hat direction. So we can use this to clean this up a little bit, and we don't know, well, we know Q2 and Q1, but I haven't written them out yet. But we can actually make this a little cleaner. K over r squared will do fine. And then we have Q2 cosine, oops, Q2 cosine theta. My apologies, we should have 2 of these. We should have 2 of these because we have 2 of these values. We did not put a 2 in front of this. So we really should have a 2 times Q2 cosine theta minus Q1. Now, just in case you missed that, I noticed that I only had one of these terms, but I should have 2 of those terms due to the presence of this x component and doubled up x component due to the other charge, right? So, my bad, I should have put the 2 in there earlier. Okay, now all it takes is just plug in some numbers in, right? 8.99 be 0.04 meters, and that's squared. We have 2 times, what is Q2? 3 nanocoulombs. Okay. And that's going to be cosine of 30 minus, do you know what the cosine of 30 is? You'll get used to this. If you haven't gotten it in Physics 1 yet, it's 0.866 over square root of 3 over 2. You could put that in for it automatically if you want, or you can just punch it in. Either way works. Q1 is a 2 nanocoulomb charge, which I'll put in SI units also. And altogether, that gives us 18,000 newtons per coulomb in the x-hat direction, positive. To the influence of both of the positive charges. The positive charges have less than their full value, but they're already stronger charges than the negative charge. And there are 2 of them, so you would expect it to win, the positive charges. If we wanted to scoot the negative charge back and forth on the x-axis, then that would actually give us a little bit of ability to adjust the E-field strength at point P. So, all right, that's part A. Clean this up. So for part B, we have already taken care of the hard part. Part B is super easy. We just use the relationship between force and E field. And that relationship, described in gold, F equals QE. The vector carries. Here, all you have to do is multiply that charge by the E field in which you have placed it, right? So what are we placing? A negative 5 nanocoulomb charge, and we're placing it at point P where we have 18,000 newtons per coulomb. Of course, we have to preserve our vector there. And so we know that this is going to have a negative force, which makes sense, right? Because it's a negative charge, it should go the opposite direction of the E field there. And that provides us with 9.00 times 10 to the negative 5 newtons. Okay, and that should be that. Clean this up a little bit. Okay, and there we have part A and part B. So check your answers, go back and